This problem is one of the best applications of various concepts in congruence of triangles and areas of parallelograms and triangles. What makes this problem awesome is that when we have finished proving all its parts, we will have proved the Pythagoras theorem, which is what this note at the bottom says, that the last result 7, is the famous theorem of Pythagoras. Okay, now let's understand this problem carefully. Here's what it says. ABC is a right triangle. I'm highlighting this triangle, ABC, right triangle, which is right angled at A. BCED, ACFG and ABMN are squares on the sides of BC, CA and AB respectively. So BCED is this square, ACFG is this square and ABMN is this square. So I've highlighted all the three squares on the sides of triangle ABC. Then the problem says line segment AX is perpendicular to DE and meets BC at Y. So I'm highlighting now the line segment AX, which is perpendicular to DE and meets BC at the point Y. Now we have to show each of these 7 parts that I've put in a box. What I suggest is that you take a few moments, pause the video and read and visualize each part carefully and think about what we are being asked to prove. Okay, now let's go through each part one by one. So let's start with the first part. You can see that I've redrawn the figure to be larger. Now in the first part, we have to prove that triangle MBC is congruent to triangle ABD. So I'm going to highlight both of these triangles now. Triangle MBC is this triangle and triangle ABD is this triangle. And we have to show that these two triangles are congruent. So let's compare the corresponding parts in these two triangles. In triangle MBC and triangle ABD, which corresponding parts can you see as equal? Well, MB from the first triangle is equal to AB from the second triangle because these two are sides of the same square ABMN. So we can write MB is equal to AB because these are sides of a square. Also BC from the first triangle is equal to BD from the second triangle. So BC is equal to BD. Again, the reason being they are sides of a square, this time the square being BDEC, this square here. And what else can you see as equal? Well, I want you to think about the angle MBC, this angle MBC, and the angle ABD, this angle. What can you say about these two angles? Do you see them as equal or not? So observe these two angles carefully. The first angle, angle MBC, is made up of two parts, and I'm going to write these two parts. As I write them, visualize them in the figure. So angle MBC is made up of angle MBA, which is this angle, and plus angle ABC, which is this angle between AB and BC. And angle ABD, the second angle that we are comparing, this angle here, ABD, this is also made up of two parts. It's made up of angle ABC, which is this angle ABC, plus angle CBD, which is this angle. So plus angle CBD. So make sure that you understand these sums carefully because this is one of the key ideas in the proof. So angle MBC is angle MBA plus angle ABC but angle MBA is simply 90 degrees because it's one vertex angle of a square. So angle MBA is 90 degrees. So angle MBC is 90 degrees plus angle ABC, and angle ABD is angle ABC plus angle CBD. But angle CBD is also 90 degrees because angle CBD is one vertex angle of a square. So both MBC and angle ABD, they are 90 degrees plus angle ABC. And this means that these two angles are also equal. So we can write angle MBC is equal to angle ABD, and this is something that we have proved just now by splitting up the two angles into their respective parts. So what we have here is two triangles in which two side pairs and the included angle pair equal, and this means that the two triangles must be congruent. So triangle MBC must be congruent to triangle ABD, and this is by using the SAS, side angle side congruence criterion. So this proves part 1. Now coming to part 2, in part 2 we have to prove that the area of BYXD is twice the area of MBC. So BYXD is this quadrilateral that I have highlighted. This is actually a rectangle because it's a parallelogram and all its angles are 90 degrees. So the area of this is twice the area of triangle MBC, which is this triangle I've highlighted. This is what we have to show in this part 2. So here's the logic that we can use to do this. So first we can compare the area of BYXD with the area of triangle ABD. So these two are on the same base BD and they are between the same parallels BD and AX. Why is BD parallel to AX? Because we are given that AX is perpendicular to DE, and of course the angle at D, angle BDE, is also 90. So we have BD parallel to AX. And this basically means that the rectangle BYXD and the triangle ABD, they are on the same base BD and between the same parallels BD and AX. So the rectangle's area will be twice the triangle's area. And we also saw in the previous part that triangle ABD is congruent to triangle MBC. So these two will have the same area. And from here it follows that the rectangle BYXD's area is twice the triangle MBC's area. So this is the logic that we will use. So in the first step we will compare the rectangle BYXD and triangle ABD, so the areas of these two. So let's write this out. So BYXD and triangle ABD, these are on the same base and the same base is BD. So same base BD, and these two are also between the same parallels, and the same parallels are BD and AX. So the rectangle's area BYXD will be twice the triangle's area, 2 times area of ABD. Okay, now in the next step we will compare the area of triangle ABD with the area of triangle MBC. So in the previous part we saw that these two triangles are congruent. So triangle ABD is congruent to triangle MBC is what we saw from part 1, and this means that their areas must be equal. So area of ABD must be equal to area of MBC. So what we have here is, from this first relation we have BYXD is 2 times area of ABD, and then from the second we have area ABD is equal to area MBC, and this means that area of BYXD is twice the area of MBC. Okay, so this is what we had to prove in part 2. Now coming to part 3, in this part we have to prove that the area of BYXD is equal to the area of ABMN. So BYXD is this rectangle that I have highlighted, and ABMN is the square on the side AB of triangle ABC. We have to show that these two areas are equal. Now this is actually quite straightforward to show. From the previous part we saw that the area of BYXD is twice the area of triangle MBC, and now we can also see that the area of the square ABMN will also be twice the area of triangle MBC, because these two are on the same base MB and between the same parallels MB and NC. So both the rectangle BYXD and the square ABMN, their area is twice the area of triangle MBC. So their areas are equal to each other. So let's write out this reasoning. So we have area of BYXD is twice the area of MBC, and this is basically simply from the previous part. So this is from part 2, and now ABMN, the square ABMN and the triangle MBC, they are on the same base. So let's write this. So ABMN and triangle MBC, they are on the same base MB and they are between the same parallels. And what are those parallels? Those parallels are MB and NC. MB and NC, and this means that the area of ABMN is twice the area of MBC. Alright, so what we have here is area of BYXD is twice area of MBC, and area of ABMN is also twice area of MBC. And from these two relations, we can now conclude that the area of BYXD, the rectangle, is equal to the area of ABMN, which is the square on AB. So this is how we can do part 3. Now part 4 is actually quite similar to part 1. We have to prove that triangle FCB is congruent to triangle ACE. Triangle FCB is this triangle and triangle ACE is this triangle that I've highlighted. Now let's compare the corresponding parts in these two triangles. So in triangle FCB and triangle ACE, which are the corresponding parts which are equal? So we have FC from the first triangle equal to AC from the second triangle, because these two segments are sides of the same square ACFG. So we can write FC is equal to AC because these two are sides of a square. And similarly, CB, this side of the first triangle, is equal to CE, this side of the second triangle. So CB is equal to CE, and these two are equal because they are sides of the same square BCED. So CB is equal to CE also for the same reason. And just like in part 1, we can now compare this angle FCB, this whole angle, with this angle ACE. In these two angles, there is this common part of ACB and the other part. So this part here is 90 degrees and this part here is also 90. So the two angles that we are comparing, angle FCB and angle ACE, they must be equal. So let's write this here. Angle FCB, this angle FCB, will be angle FCA, which is 90 degrees, plus angle ACB. So observe this carefully. And angle ACE will be, angle ACE is this whole angle. This will also be 90 plus angle ACB. So this will also be 90 degrees plus angle ACB. So these two angles are equal. Let's write this here. Angle FCB is equal to angle ACE, and this is something that we have proved. So we have two triangles in which two side pairs and the included angle pair are equal. So these two triangles are congruent. So triangle FCB is congruent to triangle ACE, and this is by using the SAS, side angle side congruence criterion. So this is how part 4 can be done, and as you can see, this is very similar to what we did in part 1. Coming to part 5, this is again very similar to part 2. in part 5 we have to prove that the area of CYXE is twice the area of triangle FCB. So CYXE is this rectangle, and it is a rectangle for the same reason that BYXD was a rectangle. This is a parallelogram in which all angles are 90, and we have to show that the area of this rectangle CYXE is twice the area of triangle FCB, which is this triangle. And to do this, we can follow the approach that we took in part 2. We can first compare the area of rectangle CYXE with the area of triangle ACE. These two are on the same base CE and between the same parallels CE and AX. So CE is parallel to AX, and this means that the area of the rectangle CYXE will be twice the area of triangle ACE. And also from the previous part, we saw that the triangle ACE is congruent to triangle FCB. So these two will have the same area, these two triangles. And hence, the rectangle's area will be twice the area of triangle FCB. So let's write out this proof. So first, we are comparing the rectangle CYXE and triangle ACE. So these two, they are on the same base. The same base is CE, and between the same parallels, and the same parallels are CE and AX. So this means that the rectangle's area of CYXE is twice the area of the triangle. So twice the area of triangle ACE. And in the next step, we will compare the area of triangle ACE with the area of triangle FCB. So we saw from the previous part, so from part 4 I think, we saw that triangle ACE is congruent to triangle FCB, right? This is what we saw in the previous part. So this means that area of ACE is equal to the area of FCB. So now we have area of CYXE is twice the area of ACE, but area of ACE itself is equal to area of FCB. So from these two equations, we can conclude that the area of CYXE, this rectangle, is twice the area of FCB. FCB is this triangle. So as you can see, this proof is very similar to what we did in part 2, and this is how we can do part 5. Now let's do part 6, which is again very similar to part 3. In this part, we have to prove that the area of CYXE is equal to the area of ACFG. So CYXE is this rectangle and ACFG is the square on side AC of triangle ABC, and we have to prove that these two areas are equal. So here's how we can do this. In the previous part, we proved that the area of CYXE, the rectangle, is twice the area of triangle FCB, and also the area of square ACFG will be twice the area of triangle FCB, because this square and the triangle, they are on the same base FC and between the same parallels FC and GB. So both the rectangle CYXE and the square ACFG, their area is equal to twice the area of triangle FCB. Hence, the rectangle and the square will have equal area. So let's write this out. So from the previous part, which I think was part 5, we have the area of the rectangle CYXE is twice the area of triangle FCB. And now we will compare the area of square ACFG and triangle FCB. So ACFG and triangle FCB, they are on the same base. What is that same base? That same base is FC, and they are between the same parallels as well. And what are those parallels? The parallels are FC and GB. And this means that the area of the square ACFG So area of ACFG will be twice the area of FCB. So what we have here is the area of rectangle CYXC is twice the area of FCB, and the area of square ACFG is also twice the area of triangle FCB. And from this we can conclude that area of the rectangle CYXC, this rectangle, is equal to the area of square ACFG, which is the square on side AC. So this proves part 6. Now finally we come to the last part of the question, question 7, where we have to show that the area of BCED is equal to the area of ABMN plus area of ACFG. So all of these three are squares on sides of triangle ABC. So BCED is this square, and we have to show that this square's area is the sum of the areas of the square ABMN and the square ACFG. Now this is actually quite straightforward to show from what we've already demonstrated in the previous parts. What we can do is we can think of the area of square BCED as being made up of two parts. One part is the area of rectangle BYXD, and we showed that this area in part 3, we showed that this area of BYXD is equal to the area of square ABMN. And the second part of the square BCED is this rectangle CYXE, and we showed in part 6 that this area of CYXE is the same as the area of square ACFG. So if you put these two areas together, you will get the area of triangle square BCED, which will be the sum of the areas of ABMN and ACFG. So this is all that we have to do. So let's write this out now. So area of BCED, the left hand side, can be written as the sum of two parts. One is the area of BYXD, which is this part. So area of BYXD, the rectangle, and the second is the area of CYXE, this part. So area of CYXE. And now the area of BYXD, this rectangle, is the same as the area of square ABMN. So instead of BYXD, we can write the area of ABMN, and instead of the area of CYXE, we can replace it by the area of square ACFG. So here we can write square ACFG. So this basically proves that the area of the whole square BCED is the area of square ABMN plus the area of square ACFG. Now if we write these areas in terms of the sides AB, BC and AC, what is the area of BCED? Well, BCED is on the side BC, so area of BCED we can write it as BC square equal to, what is the area of ABMN? So ABMN is on side AB, so the square can be written as AB square, and ACFG is on side AC, so the area of ACFG can be written as AC square. So what we get is BC square is equal to AB square plus AC square, which is basically the statement of the Pythagoras theorem. The square of the hypotenuse is the sum of the squares of the other two sides. So this basically completes part 7 of the question. So here's a simulation which shows a right triangle ABC, which is right angled at the point A, and it has squares on each of its sides. Our eventual objective was to prove that the area of the larger square BCED was equal to the sum of the areas of the smaller squares ABMN and ACFG. So you can see that I can move around the vertices of triangle ABC to change the figure if I want to. Now here's how we proceeded. So first we compared triangle MBC with triangle ABD, and we showed that these two triangles are congruent. From from this fact, it followed that the area of square ABMN would be equal to the area of the rectangle BYXD. So this was one part of our solution. And then we also compared the triangle FCB with triangle ACE, and we showed that these two triangles are congruent. And from here it followed that the area of square ACFG would be equal to the area of the rectangle CYXE. And now even if I move around this figure, you can see that these equalities always are true. So the area of BYXD is equal to the area of ABMN, and the area of CYXE is equal to the area of ACFG. And so if you put together these two areas, BYXD and CYXE, you get the area of the larger square BCED, which is equal to the sum of the areas of the smaller squares. And this basically means that BC square, the hypotenuse square, is equal to AB square plus AC square. So this is the Pythagoras theorem for you. Now finally, before ending this question, I want to show you a simulation that summarizes all that we did in this question. My hope is that the simulation will help you synthesize, it will help you consolidate all the various things that came up in this question. So in the end, I would like to say that this is a beautiful problem because it brings many different ideas quite nicely. It brings many different ideas together and ends up improving the Pythagoras theorem. The thing is that you may have followed everything I said in the video, but the real test of whether you have actually understood everything properly would be to work out all the parts once again on your own without referring to the video. So make sure that you do that. To learn more about how QMath can help you crack school and board exams, explore QMath Leap, a live online classroom program run by highly experienced and committed teachers.